Now let's look at what the transformations actually look like for the vector and the tensor cases in the complex representation, and it will make the idea of these fields being spin fields suddenly make sense. So we'll just look at our vector u and the standard basis set transformation as we had before, but we're now just going to write it in explicit components. So if you write it out, we can now make the identification that u plus is equal to 1 over root 2 times ux plus I uy, and u minus is just its conjugate. Now that has a really nice geometric interpretation, because we can just draw it in the Argand plane with beta being the angle subtended with the x-axis. And of course that's just each component, as you can see, just by virtue of Euler's formula, just gives you a simple exponential form for each one. And that means we can actually write down our transformation law explicitly in terms of exponentials, and we can visualize it, because once the vector rotates in the real representation, as in the left pane, you can see that the two corresponding components in the complex representation also rotate with the same angular frequency, but in different directions. And in that sense, the vector field u decomposes into two complex components with spin +1 and spin -1 in the complex representation. As for the tensor case, it's fairly similar, so I won't go through the algebra in gruesome detail.
Hello, Trevor from the future here. I decided in post-production that actually this derivation really ought to be shown in full, so here it is. So we're going to take the stress tensor sigma, and we're going to subtract this component, which is half of the trace multiplied by the identity matrix, from sigma, and that gives you this quantity S, defined as such. The point of S and what S is really the interesting part of the stress tensor, because it's had the scalar component, this symmetric diagonal component, subtracted from it, and the resulting definition S, when written out in full in terms of the original components, reads as follows. And if you just look carefully at the terms, you can see that there's actually only two unique terms in S, which are SXX and SXY. That's why this tensor tends to be called the symmetric traceless component, because the trace, as you can see, the sum of the diagonal components adds to 0, and it's symmetric because the off-diagonal components are equal to each other. Okay, so let's go ahead and do a rotation of this tensor using our standard real representation of the rotation matrix alpha. And what we get is that SXY tilde can be expressed in terms of the original the original components of the modified tensor S, with these sine and cosine 2 alpha relationships, which is a clue that the tensor is rotating at twice the angular velocity as it did in the real representation. We get a similar result for S tilde XX, and so in a similar way with the vector u, by making the identifications, or the definitions if you prefer, sigma +2 and sigma -2 expressed in terms of the components of the interesting part of the stress tensor, tilde xx plus I s tilde xy, that is, we'll just take these terms here that we derived earlier and write a similar linear combination to these ones here that we just identified. And with a little bit about algebra, we can see that they're actually just related quite simply. So we have s tilde xx plus I s tilde xy is equal to the original linear combination sxx plus I s xy times this exponential. We have a similar result for the other linear combination, and so we can finally identify that our sigma +2 and sigma -2, as defined above, transform really simply by this really simple exponential formula, and that's how we arrive at the transformation law for the tensor. It does consist of 3 lines, because of course we subtracted our original scalar component as on the first line, and by virtue of the fact that it's a scalar, we know that it doesn't transform at all, and so that's the transformation law for the tensor.
And see that essentially we can express the transformed tensor components in terms of the untransformed tensor components, and they're just related by a simple exponential. So we end up with this really nice simple transformation law, and that gives us this rather nice visualization, a bit like the previous time. Now we can see that the two components are spinning with angular frequencies 2 times and -2 times the angular frequency of the original tensor in the real representation. And I haven't drawn it explicitly, but in this case, if you go through the algebra explicitly, you can see that the tensor actually decomposes into one scalar component and a spin +2 and a spin -2 component in the complex domain. And then finally, our scalar, we should just include it for completeness. It doesn't transform at all, but just to put it in there, there it is. So in summary, we have the transformation laws for our vector, our tensor, and our scalar components written explicitly in terms of the really nice simple exponential form. But if you cast your mind back a few slides, you should remember that the kernel, our old friend the kernel, well, it had a similar form as well. So essentially, we've now unified the way in which we express the kernel and the physical fields, and they're all just irreducible representation, or irreps, of SO2. So we can use this really simple complex exponential form for the algebra when doing convolutions with physical fields, whether they be scalar, vector, or tensor, or stacks of those kinds of features, with our SO2 kernels with the really simple algebra of complex exponentials throughout.